Welcome to Chapter 2, Basic Chemistry. Some of you may be asking yourself, this is a biology class, why do we have to talk about chemistry? All living things are composed of the same chemicals. You will find that it's a common theme throughout the sciences that the structure of something determines its function. And if you'll recall from our Chapter 1 discussion about the organization of life, organisms are made of organ systems that are made of organs, that are made of tissues, that are made of cells, that are made of molecules, that are made of atoms. We also mentioned that the cellular level is where we first see those 6 characteristics of life emerge. So this is the basic or the fundamental unit of life. To understand how a cell functions, we have to understand those things that make it up, which are molecules. And to understand molecules, we have to understand atoms. Just like if you were wanting to be an auto mechanic, you couldn't just go out and understand a car. You would have to take the car apart to understand the various parts of the car to understand how the car functions. So to understand cells, we have to talk about molecules and atoms. We're going to go way back in your education to probably about the 4th grade, where you learned that matter is anything that has mass or takes up space. So what is matter? Everything is matter. The floor that you're standing on, your matter, the air, everything is matter. And there are 3 forms of matter found on this planet. There are solids, liquids, and gases. Solid matter has a fixed shape and a fixed volume. Liquid matter actually has a fixed volume that takes the shape of its container. And of course, gas has neither a fixed volume nor a fixed shape. So, matter, what is it? It's composed of elements, things like copper, potassium, calcium, nitrogen. These are the basic substances that make up everything else. They have specific chemical and physical characteristics, each one of them. And these are, again, are those fundamental substances that make up everything else. Matter, these elements have only one type of atom. So copper would have a specific atom type, calcium would have another atom, nitrogen would have another atom, and the atoms of nitrogen would differ from the atoms of calcium or copper. And we're going to talk about how that is later on in the discussion. But there are 92 naturally occurring elements. Don't worry about the synthetic ones. It changes, but I would like for you to know that there are 92 naturally occurring elements. So, since we're in biology, let's talk about the elements that make up living things. Living things are primarily made of carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. As a matter of fact, all living things are approximately 98% those elements. What does that mean? That means that only 2% of your mass is something other than these 6 elements. We can narrow it down even more and say that the first 4, carbon, hydrogen, and nitrogen, actually make up 96% of your mass. I think that's awesome to think about, that only 4% of your body is something other than carbon, hydrogen, nitrogen, and oxygen. So these atoms of these elements actually come together to form molecules that make up all living things. So elements have names. For those of you that have never had chemistry before, elements do have names. Some of you that have had chemistry will find this very, very basic. The names are usually Latin or English, and we have an abbreviation for those names. It's usually a 1 or 2 letter abbreviation, and we call that abbreviation the atomic symbol for that particular element. Some of them are very, very easy, such as carbon. Is the atomic symbol of carbon is C. The atomic symbol of hydrogen is H. The atomic symbol of oxygen is O. So those are pretty easy until you come to the elements that have these symbol names for their Latin names, such as sodium. Sodium's Latin name is natrium, so the atomic symbol is Na. Iron is ferrous, so the atomic symbol is Fe. Potassium is K. Nitrogen is N. And sulfur is S. These are some common elements that are found in living things that you need to remember the atomic symbols of. We arrange the elements in something called the periodic table. Some of you are probably familiar with this. We start with element number 1, which is right here. That's hydrogen. And notice that there's a number up in the upper left-hand corner right there telling me what the element number is. So that is 1, that's hydrogen. We have to come way across over here to helium, that's element number 2. Lithium is 3. Here's element 4. We skip across. Here is 5, 6, 7, 8, 9, 10. And you just continue in that manner. Very important to realize that the table is in atomic number order. And we'll talk more about what that is in just a moment. So, what is an atom exactly? An atom is the smallest particle of an element that has the properties of that element. So it's the smallest I can go. If I have carbon and I break it into smaller and smaller and smaller pieces, it's the smallest I can go, and that element still act and react like carbon. If we go below the level of the atom, again, this would be very, very small, we call those things subatomic particles. Sub means below. Atomical refers to the level of the atom. So when I start talking about the components of an atom, we call those subatomic particles. And atoms are made of electrons, protons, and neutrons. And notice in this illustration, I actually have them color-coded. So you see that the protons and neutrons are actually in the center of the atom, and the electrons, which are yellow, are orbiting around that nucleus or center of the atom. So protons, neutrons, and electrons. So let's take a look at the atom, and let's talk about the properties associated with these particles, because they do have properties associated with them. Notice now that my subatomic particles are not color-coded. They actually have charges associated with them in this illustration. So let's take a look at them. In the center of the atom, right here, you see there are pluses and zeros. Those are representing the protons, which have a positive charge, and the neutrons, which are neutral. So our protons and neutrons are in the center or nucleus of the atom, right there. Okay, notice that the electrons are on the outside, and they actually have negative charges associated with them. If you were to look at this atom and take it over to the scale and determine what it weighed or what its mass was, most of the mass would come from the center of the atom. Notice the relative size differences between the particles. So we actually do call the center of the atom the atomic weight of the atom, or the atomic mass. Atomic weight or atomic mass is the number of protons added to the number of neutrons in the atom. And if we're going to illustrate it, we use the atomic symbol here, and our mass would be as a superscript to the left of that atomic symbol. So that illustration is telling me that carbon has 12 particles in its nucleus. Atomic number, on the other hand, that number which the periodic table is organized by, is the number of protons in the atom, right there. So we would illustrate, if we were writing it, we would say this is the atomic symbol, this is the atomic mass of carbon, which is 12, and this is the atomic number of carbon, which is 6. Okay, so remember, atomic weight is protons plus neutrons. Atomic number is just protons. So the difference between the two would be the number of neutrons there. Very important to realize that, because the atomic number of protons, the atomic weight, protons and neutrons, and if we want to subtract those two, atomic number subtracted from atomic weight, we would have the number of neutrons there. So very important to realize that, because there are naturally occurring isotopes of some of these elements. An isotope is an atom of the same element that has the same atomic number, which is the number of protons, but different atomic weights, meaning that isotopes have different numbers of neutrons. Now, the atomic number defines the element. Let's take a look at this example. What you're looking at here is lithium. Atomic number defines the atom. And that's what makes one element different from the other, is the atomic number. Lithium's atomic number is 3. And that means it has 3 protons in its nucleus. Excuse me. So this is lithium. This is normal lithium. It has an atomic weight of 6, meaning that it also has 3 neutrons. Lithium is found in nature with an atomic number of 3 and atomic weight of 7. It's still lithium. Remember, the atomic number defines the element. So it's still lithium, but it has a different number of neutrons than lithium with 6 as an atomic weight. Lithium-7 would have 4 neutrons in its nucleus. This is another isotope of lithium here. Its atomic number is still 3. Remember, atomic number defines the element, but this lithium has an atomic weight of 8, meaning that it has 5 neutrons in its nucleus. All 3 of these are lithium. They're isotopes. They have the same atomic number, but different atomic weights. These isotopes are very unstable, and they tend to want to break down. The nucleus here of lithium-8 is very large compared to the nucleus of lithium-6 there. So these isotopes start throwing particles out of their nucleus, trying to get rid of some of that weight. Those particles are called radiation and can be dangerous. We actually use some isotopes in medicine. Barium is an isotope that's used in medicine. We also use isotopes to determine the age of fossils. Some of you may have heard of carbon-13 and carbon-14. Those are isotopes of carbon that have more neutrons in their nucleus than normal carbon-12. So we've talked about protons and we've talked about neutrons. Let's talk about electrons now, because the electron, the number of electrons and how they're organized in an atom determines the properties of that atom. It determines how that atom will act and react. First of all, make sure that you remember that naturally occurring atoms are electrically neutral. Now, what does that mean? That means that if an atom has an atomic number of 8, meaning it has 8 protons, it's also going to have 8 negatives, 8 electrons, because in nature they are electrically neutral or balanced. So, number of electrons equals number of protons. I want you to realize that the electron is where the energy of the atom is. So from now on, when you hear the word electron, I want you to think energy. When you hear energy, I want you to think electrons. Looking at these 2 examples here, these 2 atoms, the electrons all look the same, and they are. Electrons all have the same weight and they have the same charge. So if I were able to take the electrons out of those 2 atoms and look at them in my hand, I wouldn't be able to tell them apart. They all are the same. But what makes electrons different, one electron from another, is their charge, their energy content. They vary in energy content. They have the same weight, they have the same charge, but the energy content in the electron is determined by where that electron is, where it's located in its atom. So the ones that are farthest from the nucleus have the most potential energy. So these electrons on the outside of this oxygen atom would have more potential energy than the electrons in the closer to the nucleus of that particular atom. So, electrons, where are they found and why are they organized like they are? Well, they're found in orbitals, and for our purposes, I want you to understand that an orbital is anywhere an electron might be found. But within that orbital, the electrons configure themselves or arrange themselves in shells, sometimes called energy levels. Take a look at this calcium atom right here. Calcium's atomic number is 20. That means it has 20 protons. Well, it's electrically neutral, so it also has 20 electrons. Well, you can take a look at this atom and see that 2 electrons are really close to the nucleus, and then as you go to the next energy level, there are more electrons in that energy level, and so forth and so on. the electrons arrange themselves in what we call the octet rule. The first energy level, that first shell closest to the nucleus, fills up with 2 electrons. No more than 2 electrons can be in the first shell because of their properties. Negatives repel each other while they're being attracted to the 20 protons in the nucleus. The next shell and subsequent or other shells beyond that fill up with 8 or multiples of 8 electrons. So 2 in the first shell, 8 in the second shell. And it's full, and then you go to the third shell. Let's make sure you understand that. Take a look at this carbon atom right here. Again, carbon's atomic number is 6. That means it has 6 protons. It also has 6 electrons. With 6 electrons, the first shell fills up with 2, and the remaining 4 electrons would be pushed into the second shell. Let's take a look at oxygen here. Oxygen's atomic number is 8. 8 protons in the nucleus. That means it has 8 electrons. First shell fills up with 2, and the remaining 6 electrons would be pushed to the second shell. Here's sulfur. Sulfur's atomic number is 16. 16 protons, meaning it has 16 electrons. With 16 electrons, there would be 2 in the first shell. That gives you 14 left. The second shell would fill up with 8, and the remaining 6 would go into the third shell. So first shell's full at 2, second shell's full at 8, third shell's full at 8. It's not until you get to the bigger atoms that there are actually multiples of 8 in the shell. The properties of the atom are determined by the number of electrons located in the last shell, in the outer shell. And from now on, we're going to call that outer shell of the atom, whichever shell is the outer shell, we're going to call it the valence shell. So when the valence shell of the atom is not full, that means that the atom will react with other atoms. If that valence shell happens to be full, the atom will not react. It's stable, and we call that inert. So if the outer shell, the valence shell, is full, it's not reactive. It's inert. And all of these inert elements are located right here in this column of the periodic table. You may have been wondering why we skipped all the way from hydrogen to helium over here. It's so that we can get all of the inert elements in this column. Think about it for a moment. Helium's atomic number is 2. What's the valence shell? It would be the first shell, and it is full with 2 electrons. Here's neon. Its atomic number is 10. With 10 electrons, you would have 2 in the first shell and 8 in the second shell, so its valence shell is also full. Here's argon. Its atomic number is 18. Again, the valence shell is full. So, atoms like full outer shells. And when they are near other atoms that do not have a full outer shell, they oftentimes interact so that both atoms can get a full outer shell. They want to be stable. They want a full outer shell. And so they may actually give up electrons to another atom to get a full outer shell. They could actually accept electrons from another atom, or sometimes we even see atoms sharing electrons so that both of the atoms actually think that they have a full outer shell. When atoms give up, accept, or share electrons, they're interacting with each other by sharing or giving up electrons. We call that chemical bonding. When atoms bond, it results in something that we call a molecule. That's the smallest part of an element or compound that has the properties of that element or compound. And a compound is actually 2 or more different types of atoms that react or bond together. For our purposes, we'll probably use those terms interchangeably. So, when we show that atoms have bonded together, we have to illustrate or write that using their atomic symbols and the number of atoms of each element it took to make that molecule. So, for instance, one that you're very familiar with, maybe not, hydrogen chloride here, and water. Water you should be familiar with. Notice that our symbol for the composition of hydrogen chloride is HCl, and notice there is no subscript there. That's telling me that to make a molecule of hydrogen chloride, I need one atom of hydrogen and one atom of chlorine. If there is no subscript, it's an understood one. To make a molecule of water, I need 2 atoms of hydrogen and 1 atom of oxygen. To make a molecule of water, H2O, it takes 2 hydrogens and 1 oxygen. So, very important, energy relationships. When atoms interact with their electrons, they actually have formed an energy relationship. Remember, the electron is where the energy of the atom is. Atoms are not typically going to just jump on each other and give away electrons. It's going to take a little impetus to get them to join together. So it takes a little energy to form a bond. Reactions don't automatically happen. They have to have a little push. It takes energy to make that happen. Once the atoms have bonded together, once they have that relationship with their electrons, the energy is actually stored in those bonds. Very important concept in life science. Energy is stored in chemical bonds. When atoms come together and bond, we have energy stored in that molecule right there. We call those reactions anabolic. When we're building molecules, that's anabolism or anabolic reactions. And again, it takes energy to make that happen, and the energy is actually stored in that molecule right there. So if I have this molecule right here and I want to get energy out of it, how do I do that? Well, I break those bonds. So energy is released when the bonds are broken. Those reactions are referred to as catabolism or catabolic reactions. If I take a molecule and I break the bonds and I'm getting my atoms, I'm releasing energy. Anytime energy goes into a reaction, we refer to that reaction as being endergonic. And when energy comes out of a reaction, we refer to the reaction as being exergonic. To show that a reaction has taken place, we actually use the atomic symbols for those elements and the numbers of atoms that it took. Looking at this reaction right here, and the reaction is indicated by the arrow, it's showing me that 2 molecules of hydrogen reacted with 1 molecule of oxygen. A molecule of oxygen would have 2 atoms, and it produced 2 molecules of water. So everything that goes into a reaction, all of those things that are on the left side of the arrow are called reactants. The products are on the right, and those are the substances that are produced by the reaction. So reactants on the left, products on the right. And we're going to see several different types of reactions in the next few weeks. We've already talked about a reaction that would synthesize or produce a molecule. So synthesis reactions are when some atom A or molecule A reacts with another molecule or atom to produce AB. These are just generic. These are not chemical symbols, but you're producing a molecule there. Decomposition is when you're breaking something down. In this example, we have some molecule AB that's actually broken down into its components, A plus B. Sometimes we have reactions where the atoms just change places. Those are called exchange reactions. Some reactions are reversible, meaning that it's a synthesis and a decomposition at the same time. We have one very, very important reaction involving ATP, where ATP is actually produced and broken down simultaneously. We also will be talking about reactions we call oxidation reduction reactions. Sometimes these reactions are referred to as redox, R-E-D-O-X. In these reactions, oxidation would be the loss of an electron. So an electron is loose. And there's always going to be a reduction reaction to accompany that. Whenever an electron is lost, there's always a reaction that takes it. Reduction is the gain of electrons. So we'll talk about those types of reactions later.